Thank you. Let's implement a new application. This is how the application looks like. Yeah, it's a complicated and rather large enterprise application. It consists of some domain objects, yeah, shown as the colored rectangles here, and it implements some business logic on these domain objects. Of course, the application needs to persist the work it does by storing the domain objects in some persistent storage. Yeah, the persistent storage is most likely some kind of database product. We need to find a way to store the information contained in our domain objects and move them over those grayish arrows, yeah, to the storage system. But not just move the data, but also convert or transform the data into a representation that is more suitable to be stored. And of course, yeah, we also need to move the data back again, the domain objects back again, yeah, and move them from the storage, transform them back, and move them back into our domain representation. Yeah. This separation is useful, of course. Yeah, it decouples the domain logic from our storage, allowing both to change independently. And of course, also, our users want to interact with our application through some kind of user interface. Yeah, maybe we are working on a client-server application, a web application with a web front end, like the kind of client-server architecture that is typical nowadays to structure software applications. Yeah, for the users to be able to view and to manipulate our application's data, we need to move the data across the greenish arrow. Quite hard, yeah. Again, this requires that we convert our data structures in a format that is more suitable to be serialized, to be able to transmit the information via the network, in a format like JSON, for example, or EDN. And of course, back again. This separation also is a good thing. Yeah, it decouples the domain model from the presentation layer, allowing both to change independently. And additionally, the application may need to use some other services that also requires the data to be restructured to match the interface requirements of the service and to be transformed into a serializable format if the service wants to be contacted via the network and back again. So in a typical application, yeah, we have many of these two-headed arrows to implement. We, as software developers, have to consider and implement many conversions and transformations. In practice, this is likely to be a tedious and error-prone task. Let's look at the storage part first. Yeah, the application needs to persist the information. The storage is most likely some kind of database. Yeah? How to approach the two-headed arrow there. So, in a typical, maybe object-oriented setting, your answer might be to use an object relational mapping solution, or ORM solution, that provides a framework for mapping application domain objects to the relational database tables and vice versa. For example, in the Java world, there is a very popular Spring Boot framework that comes with the Hibernate ORM library out of the box. But we have them also on the functional side. Yeah? They exist in the functional programming world as well. Popular examples are Beam for Haskell, Slick for Scala, and Toucan for Clojure. Yeah, and this is how that looks like. I chose Java here. This is an example, Spring Boot Hibernate. Yeah. Here, We have the definition of a class for a domain object called user. Yeah, the user is a composite data structure that consists of some unique ID, a username, a user's password, and user roles. The user roles are represented as a list of roles. Yeah, and below is the definition of a role data structure. Yeah, the role consists, again, of a unique ID and a name of the role. Spring Boot uses annotations. These are like the pinkish lines with a at in front to mark the objects and to relate it with the database. Yeah? So both the objects are marked as entities. Yeah? So Hibernate creates a database table for each entity, here for users and for roles. Yeah? The ID field in each class definition is marked as @ID and @generated value. Hibernate will use this information to have the database create an ID column and a primary key together with some strategy to generate values for the primary key. So I've omitted a lot of code here. Yeah. There's just not enough space on the slide, which is typical for Java code. There are benefits in using ORM. So like the most prominent feature and most important benefit is that it saves a lot of development time. And, well, I don't know. I cannot think of anything more. There are many shortcomings to using ORM that cause many problems during the life cycle, the whole life cycle of an application. Yeah? It is often an inadequate abstraction. It violates software development principles like single responsibility and separation of concerns. And it fails to hide implementation details as the relations leak through to the domain objects models. Not because the domain model demands it, just because it makes the integration with the ORM system easier. Like the ID field is such an example. Yeah? So it leads to incorrect abstractions in our data model. Like maybe you heard of that, ORM solutions, they tend to suffer from the object relational impedance mismatch. Yeah? SQL may leak through also. Yeah? For more complicated queries, you still have to use and write SQL. All this fosters high coupling, and high coupling is always bad. Yeah? It means that changes in one part of your application forces you to change quite a different part of your application as well. Yeah. Additionally, ORM is difficult to test. Yeah? It's impossible to write unit tests. Yeah? Instead, we can write some integration tests, bring up the test version, the test product of our database, connect the whole application to that. Such tests will, of course, be rather slow. And what we are testing, are actually having nothing to do with the database model domain object, is the database implementation as well. So it's really not that useful, and even leaving the software design principles aside, the resulting database interactions with ORM are going to be slow, especially if your application becomes large. ORM often tends to produce subpar database queries. So ORM is widely considered an anti-pattern. It initially appears to be beneficial, but in the long term has more bad effects, more bad consequences than good ones. And there are more proven and reliable solutions, alternative solutions. Yeah? So the way to go is to encapsulate your relational queries into a custom-made data access layer, or a model layer. But design the API to that layer to serve the specific needs of your domain objects, of your domain model. and resist the temptation to generalize too far. Otherwise, you would just produce another ORM. So here for us, it means that we do not get gifted this arrow. Yeah. We have to take care of this double-headed arrow between the domain objects and the storage system ourselves. Now let's look at the other arrows in our picture. Yeah. So the arrow on the left-hand side transforms and converts the domain objects to and from the user interface, and the arrow on the right-hand side transforms and converts the data, the domain objects, to another service. Yeah? So again, in your typical object-oriented programming language or the framework you are using, your answer might be to use data transfer objects, or DTOs, to achieve the task. Martin Fowler came up with data transfer objects. He described them first. So he explained that the pattern's main purpose is to reduce the round trips to the server by batching multiple parameters in a single call. So the idea is to reduce the network overhead for remote operations. And another benefit is the encapsulation of the logic that serializes to and from the format that can be transmitted or that can be stored. Yeah? So it proves a single point of change in the nuances of the serialization. And it also decouples the domain models from the data and from other layers of an application, allowing all to change independently. Yeah. So all in all, this is very useful and this is sound. Yeah. Let's look at an example. So on the left, we see our domain objects, user and role. Yeah, and on the right, we see the data transfer objects for those two domain objects. So in our DTO, we pack together the user with the roles. And we represent the roles as a list of strings instead of a list of role domain objects. Yeah? So this matches the idea to reduce the round trips. Yeah? Instead of maybe querying each row separately, yeah, our DTO bundles all the other user information together. Yeah? And to just use simple data structures like strings and lists instead of the custom data types makes it straightforward to transform such a data structure to a format like JSON. So now let's look at the implementation of the arrow. Yeah? The original DTO pattern recommends to use a mapper class to implement the mapping between the domain objects and the DTO objects. So what we immediately see here, just by squinting our eyes, that we have to implement the conversion logic between those domain objects and the DTOs twice, like once for each direction, and that those conversions look very similar. Yeah, so actually, we have to implement two arrows. Our first method converts the domain object to the DTO object. Yeah, it does that by extracting the name and the password from the domain object, and then it iterates over the roles in the domain object and extracts the name. Yeah, it then returns the DTO object by passing all those arguments to the constructor. The second method is the dual. Yeah, it converts the DTO object back to the user object. Yeah, it gets the name and the password. It iterates over the roles. Yeah, now they are strings. They have to be made into the domain object role first, and then everything is packed together, and we have our domain user object. So even for this simple example, I already feel annoyed when I have to look at the code, not even speaking of having to write that code. Yeah. It is so much code duplication. Yeah. It is tiresome, it is error-prone to maintain this code base. Creating this or extending this screams for many copy and paste related errors because, yeah, to be honest, who wouldn't use just copy and paste and trying to fiddle that code? And in reality, it is even more awful than in this simple example because our objects in the real world are more complicated and we have many more domain objects where we have to do something like that. So aside from me being personally insulted by that code, it violates, again, one of the most basic principles in software development, which is try. Don't repeat yourself. Yeah? We do not want that a change requires us to make modifications and adapt code in more than one location. Yeah? We do not want wet. We do not want to write everything twice. And we may have a lot of DTOs in our system, and there's a lot of errors to implement. So this is how the overview of our application actually looks like. Yeah, we have to take care of each direction of the originally double-headed arrows. And of course, we may need to do that for more than one domain object. We really need to reduce repetition, and we have to avoid redundancy. And this is just another case where the elegant solution exists in functional programming. What we need is a powerful abstraction called functional lenses or just lenses. There are plenty of capable libraries in all major functional programming languages. Yeah, I just listed a few. There is Ether for F#, Monocle for Scala, Control Lens for Haskell, and Active Closure Lens for Closure. So I choose Closure for this talk, and I promise you, you can be sure you won't be seeing any more Java code from me for now, today. Here is what the user domain object example implemented in Closure looks like. Yeah, so here everything fits on one slide, yeah, what we are used to with functional programs. Yeah. In Closure, we model our compound data by using records. Yeah, the first defined record type expression defines a record of type user. Yeah, this expression makes a binding make user, yeah, our constructor, that can be called with the fields in the order of the fields that are given here. Yeah, we have the field name, password, and roles. Yeah, we have selectors, yeah, user name to access the name, user password to access the password, and user roles to access the roles. And we have a predicate, user question mark, which makes it useful to distinguish users from other data structures, for example, when we use mixed data. So the next defined record type defines a type called role. Again, we have a constructor that accepts the name. We have a predicate role question mark, and we have a role name. And on my slide, yeah, at the bottom, we see example usage. Yeah? Right, yeah, we define Mike, yeah, as a user with a name Mike, a secret password, and a list of roles, yeah, where one role is here is the manager. So the highlighted fields, they can be used to the highlighted expressions here. They can be used to access the fields of the data structure. They can be used as selectors, getters, and they can even be used as setters. And they are also lenses. But what are lenses? Yeah? Lenses allow to focus on specific parts of a data structure. Here, the lens user password focuses on the password field of our user data structure. You can yank a lens over a data structure to get the value of the field that the lens focuses on. Here, the call to lens yank, with the arguments Mike, our example user, and the lens user password returns Mike's secret password. Though the syntax here, lens slash, references our namespace of our library, of our lens library. With lenses, you can also modify the focused value within a data structure. Of course, we functional programmers know that modifying is not a side effect. We do not mutate something in place. Our data structures, they are immutable, so modifying in functional programming means that we are creating a new data structure that contains a new value at the focus. So here, the call to lens shove, with our Mike user and with our user password lens and a new password, shoves the new password into Mike's user data structure. It basically returns Mike's user data structure with the password changed. So nothing too special so far. We already have ways to access fields and to modify fields. We already have the functionality to work with our data structures. But lenses can do more. And the most powerful property of lenses is that they are composable. That means we can combine our lenses and build bigger lenses out of our smaller lenses. Or the other way around, staying in the metaphor of optics, we can increase the focus of our lens, or we can sharpen the focus by combining lenses. One useful combinator is greater than. It concatenates lenses from left to right. So let's try to understand what this expression does here. The first argument, user roles, it focuses on the list of user roles in our data structure. So when we concatenate a lens that focuses on the first element of a collection, this is what the lens at index 0 does. When we concatenate that to the user roles, we sharpen the focus from the whole list to the first element in the list of our roles. And then again, when we sharpen the focus even more, when we concatenate the role name, the role name focuses on the actual name, the string in our role data structure. We have a lens that sharpens the focus on the role name of the first role in our user data structure. And we can use that composed lens like the lenses before. To use it more conveniently, we give it a name, first role name, and then we can length the lens over our data structure, and we get manager back. And of course, we can also shove a new value into our lens focus. When we shove admin into the lens focus of our Mike user, so we get the Mike user with the role name admin instead of manager. So lenses are very useful. They scale to large data structures because they uncouple the how to access data from the action of doing so. And this uncoupling, this allows lenses to compose the how to access. And there are many useful lens combinators in the existing libraries, and once you get the hang of it and been able to wrap your head around it, it is not that hard to specify your own lens combinators. So lenses define a very useful algebra. And the closure lenses I'm showing you here are actually also functions themselves. So makes them even more convenient to use. Yeah? So instead of having to yank explicitly, you can just call the lens with the data structure to get the data out, and you can just call the lens with the data structure and a new value to shove a value into the data structure. Yeah? So no need to yank and shove explicitly. So lenses are exactly the ingredient we need to achieve our goal of writing bidirectional data transformations. Yeah? Writing those transformations just once. Because lenses can be combined to projections. So this graph shows a bijective mapping, yeah, which is a mapping between two structures. We have a blue structure and we have a yellow structure. And the dots are the elements in the structures, and the arrows, they show the mapping between the structures, between the elements, to be more exact. And the arrows, they point in both directions because they can be reversed by an inverse mapping. So like simple math, yeah, and that's what we'll use for our bidirectional transformations. Yeah. Because this fits exactly our problem. Yeah. We have two structures. Yeah. Here on the right is the user domain object, and here on the left, this is user DTO object. It's a new record definition. Yeah. As before, it defines the user DTO record with a constructor and the fields, and with a predicate. Yeah. Again, name, password, and the role names this time. Yeah. And these are the arrows of the projection of this particular case. Yeah. These are the arrows we need to define, the relations we need to implement to specify the back and forth mapping between these two data structures. Yeah. And with the help of projection lenses, you can actually specify these relations as straightforward as possible. So what you see here in the highlight is the actual specification. Yeah? This is a closure map. Yeah? A closure key value data structure. Each line represents a key value pair. Here we use that representation to connect the lenses that connect the fields. So the lens user DTO name, yeah, connects to the username of the domain object. And the lens user DTO password connects to the user password lens of the domain object. And the user DTO role names lens of the DTO connects to something a little bit more complicated. This is due to the fact that our application contains separate domain objects for user roles. And recall, we've decided, just in the spirit of DTOs, to not use a separate representation for the role names in the DTO. Just the strings representation is sufficient for our example. Yeah. But we can even express that as a lens. So again, here on the right-hand side, we have now a lens combination, a concatenation of lenses that concatenates the lens that focuses on the user roles, with a lens that focuses on the names, that maps this lens over the focus the user roles gave. So lens mappel is map lens. It maps a lens over a collection. So this lens combination here gives us focus on the string representations of the name. So really just the role names as strings. And this is actually all that is needed for the bidirectional projection between these two data structures. So the actually working code, it looks like this. We define the lens, user to user DTO, Yeah? And remember, since lenses behave like functions, we can just call this definition like we would any other function. And we use the projection lens combinator for the lens. Yeah? The first argument constructs like an empty user DTO object. Yeah? So this is like this is used as the target for the projection. So you can see that like as the neutral element, so to speak. And the second argument is the map that connects the fields. And below, you can see how to define the other direction, how to define the dual. Yeah? And the dual is just another lens combinator that inverts lenses. Lens algebra for the win. Yeah? So you have just to invert the user to user DTO lens to get the user DTO to user lens. And here again, here you have to specify an empty domain object, so it's the neutral element on our domain side. Yeah, and that's it. Yeah. And of course, there are abstractions for the dimmed out parts, the technical details that are not that nice, but that can easily be hidden. Yeah. Hiding these makes the implementation even more concise and the benefits even clearer. Yeah. With bidirectional transformations, you only have to specify what really is important, and you only have to specify it once. Yeah. This code comes to the point. It is easy to read, it's easy to understand, it's easy to maintain. And we can easily extend that. Yeah? It's beautiful, right? Yeah? And we can make it even more beautiful. Yeah? Like the technical details vanish once you let the record generate your projection lens. Yeah, so here we specify that our record definitions for user DTOs should also yield a projection lens, and the projection lens will be called into user DTO projection lens. And using such a projection lens makes it easy to define the bidirectional transformation. Here in the example, we define the transformation from and to EDN, like the typical closure data transfer format. But of course, this also works for record data structures or any other data structures. Yeah. To convert to EDN by using the generated projections, you just have to specify the keywords of the different fields in the same order of the record. Yeah. And again, reverse is just the inversion. Yeah. So it looks like this if you use that. Yeah, you can just call the EDN to user DTO lens with the user data structure, and that evaluates to the EDN representation. Yeah, here to our keyword, simple keyword value map. Yeah, and of course, it is bidirectional. It also works the other way around by just inverting the projection lens. And lenses compose elegantly. Here are two more examples. Yeah, we can define a lens that hides like the DTO representation. Yeah, it concatenates our user-to-user DTO and our user DTO to EDN, and this way we have like totally left the DTO outside. We've hidden the DTO, and it's as easy as just concatenating those two lenses. Yeah. And lenses are powerful. We can, they are flexible. You can express everything. Yeah. We can even use the lenses for projecting mixed data structures, like mixed recursive data structures, like here trees, for example. Trees that consist of tree nodes and tree leaves, and the nodes contain like the trees again. And here we distinguish which lens to choose by using the record predicates. So lenses can express all your transformation needs. So now we don't have to repeat ourselves when we are implementing the many double-headed arrows in our application. Thanks to the ideas of functional programming and bidirectional projection lenses. This is just another example where the ideas of functional programming improve real-world software development. I am Marcus, my pronouns are he, him, and I am a software architect at Active Group. We do software development, we do consulting, and we offer trainings. For example, we are ISA QB certified and offer certified trainings. Our specialty and our strength is that we use functional programming in all of our projects and that we employ functional software architecture. Yeah. Additionally, we run the biggest German-speaking blog about functional programming, and every year, every spring, we host the Bob conference in Berlin, and I hope to see you there. And now, with some time left, I'm happy to take some questions. Thank you very much.
Thanks for your talk. I have a question. In your example, you were lucky that the inversive operations are trivial. You have a bidirection by default because row name is both getter and setter. But I can imagine that it is not the case all the times, and you need to somehow specify the opposite direction, like if you would have IDs in your data object, data transfer object, and you need to do some search for it. Is this a common case or something like that?
So it's quite hard to understand here over the PA, but I think you're asking if there might be some special data types that require that we have to specify the conversions both ways anyway. And what was your example? Like IDs or?
For example, if a data transfer object, you have IDs instead of names, you need to do some search to get the actual object for the ID. Because in your example, role and row names are generally almost the same, with exception it's wrapped.
Like the string representation. Well, of course, yeah, it depends. Yeah, there probably might be. There are cases where you need to actually write a little part of such a transformation in both directions. Yeah, I'm not sure with the IDs. Yeah, I think you can get around that. But one example would be like date formats. Yeah. So if I want to serialize my data structure that represents like a UTC date, yeah, and I want to convert it into a string, of course, then I would have to specify how to convert that string back in a UTC data structure, data structure. But you can also do this with a lens, yeah, of course. But then you have to specify both directions. Yes. You're right. Good question. Yeah.
Hi. So I have a question about where does this break down? Because most of attempts at doing something elegantly have their edge cases and break down at some point. So where would that be the case with lenses? And in particular, what would happen, for example, if I had some field where I cannot just take a look at its counterpart, but where I'm trying to parse some, so where I have to inspect other fields of the data structure to figure out how to interpret it, how to map it back?
So first question, I don't think it breaks down. It's an algebra, yeah, and we have not found the point yet where it breaks down. Yeah, so like most of our ideas here, they exist and they surface because I was just tired of writing all this code. Yeah. So actually, I did not write the Java code, of course, but even in functional programming languages, yeah, I had to write this twice, and it was just whenever I am annoyed, I do not want to repeat myself. I do not want to write code. I do not want to write code that I don't want to write. I try to find an abstraction. Yeah. And this works, and with that, you're fast, and actually, it's also like a very good documentation form, because you're describing how the parts of your data structures actually fit together, and that works. Yeah, it just works. So, what was the second part of your question? Sorry.
Yeah, the second part was what would happen if you had a situation where you cannot just do a straightforward mapping, but for, I don't know, maybe you're working with a legacy system, or for some reason you cannot say, okay, this is how I map the username back, but that might depend on, I don't know, what the role is, for example.
Well, your lenses are usually small, yeah, and you combine them, and then you can, of course, just use a part of a lens to debug like a message or something, when I understand you correctly, or part of a string. Or
to put this another way, so if you have a bijection between your DTO and your internal model, this works well. What happens if in some cases it's not a bijection? Right, so if you have two values on one hand that you want to map to one value in your inner model, but when you map them back to the DTO, you want it to hit just one of those values.
So I think it goes in the direction. If it's not like a one-to-one projection, there are lenses where we can explicitly specify both directions.
Yeah, so something that is not fully reversible.
Yeah. So maybe we can take that offline and we can come up with an example together, and maybe I can show you a solution.
All right.
Yeah.
Thank you.
All right, we don't have enough time for next question, so let's thank Markus again.
Thank you.